Okay, so I'd like to thank Tao and Hotech for inviting me to give this talk. I tried to, and Rosario. I tried to give a cryptocurrency talk, but and Tao and Hotech were insistent that I give a tutorial on trusted hardware. And so I have a soft heart, and if you persist hard enough, you'll get it. So here's the talk. This is based on a latest what's so-called systematization of knowledge paper, and joined with a bunch of my colleagues and students. Okay, all right. Okay. So there have been many secure processors that have been built both in industry and in academia. If you have even been vaguely following the area, you might have heard of the latest buzzwords such as Intel's new SGX technology. And there's also ARM's Trust Zone, and a little less recently, there's the Trusted Platform Module, or TPM for short. And in academia, there's just a variety of secure processors that have been demonstrated. Okay. So, all right. So here are the questions that I get asked frequently. Since there are so many trusted hardware secure processors, what do they actually offer? How do the non-trusted processors compare with each other? And my favorite question is does trusted hardware obviate modern crypto? Can we just use trusted hardware to do things like secure multi-party computation, homomorphic encryption, and so on and so forth? Okay, so since there has been so much work on trusted hardware, why haven't they been widely deployed in real-world applications? What's wrong, and what do we need to do to make it right? And also, what formal abstractions do they offer? Okay. All right. Okay, so if you have ever wondered about any of these questions, the good news is that you're in the right talk. And the bad news is that because I only have half an hour, I'm only going to be able to answer a subset of these questions, not all of them. And really, this is just a teaser to our systematization of knowledge paper, as well as a research seminar course that I'm going to teach next semester. So if you are interested in this topic, please check back for the release of our paper, as well as our online course materials. Okay, so I'm just going to go and then as far as time allows, and please feel free to interrupt me if you have any questions. Okay, so, oops. Okay, so part of this talk, as well as our SOK paper, aim to explain trusted hardware to people who are not architects. And also, we'd like to help bridge the architecture community and the crypto community. So we want to help explain commercial trusted hardware to cryptographers. And we would like to promote a synergy between crypto programming languages and architecture communities. And that's where I think all of the exciting work is. And it takes the collaboration of these communities to make trusted hardware really practical and ubiquitously adopted in real-world applications. Okay. So I'm going to begin with really the simplest question: what is trusted hardware? Okay. So we are going to together do this exercise. We are going to try to recreate the process in which trusted hardware was designed. So in the beginning, as we all know, there was the Big Bang, and then computers were made. Okay, so this was exciting. Okay, once we have computers, we have this big problem. So we have this precious little computer, but we have multiple users and multiple applications that want to timeshare the same set of physical resources. Okay, so how can we do such sharing? It turns out, as the story and the legend goes, there's this small group of people in the community called computer scientists, they're also called the sages, and they designed the operating system. And what does the operating system do? The idea of the operating system is that it will help you to manage the physical resources, and it will allow these multiple applications to time share the same set of physical resources relatively easily. From the perspective of the application programmer, each application sees its own abstract machine. Okay. Well, now we have multiple applications. We also have security problems, right? So imagine one of your applications is a sensitive banking application that has your, let's say, credit card numbers, and your other application may be, an online gaming application. So I don't want my credit card number or my banking password to leak to this online gaming application. And therefore, ideally, we want to build this perfect wall in separating these different applications. And how do we do that? Obviously, the task will fall on the operating system. Okay. So the operating system must enforce isolation in between these applications. And this seems fine, only that there are some drawbacks, which I'm going to talk about. The first drawback is that this really is easier said than done. How do we enforce isolation? It turns out that enforcing isolation is really tricky. And as many attack papers in the security community have shown, existing operating systems and virtual machine monitors, they don't do the job very well. And in fact, there's a lot of information leakage through shared resources, either at the OS level or at the CPU level, right? So these multiple applications will be sharing the same operating system and the same CPU. So there are tons of attacks like this. I'm only going to highlight two of the classical attacks. So this is a recent paper by Suman Jana, who's actually a faculty here at Columbia, and Vitaly Shmetikov. And what they show is that suppose you have your Android phone. Okay, now I want to run multiple applications on my Android phone. So as we all know, the Android phone runs a modified version of Linux as the operating system. So one application is my browser, and another application, let's say, is a zero permission gaming application. You'd think that these applications are isolated from each other, but no. In fact, this zero permission gaming application can actually learn exactly which web pages you are visiting. So think about the time when you go to these sensitive websites, and that can be learned by this zero permission gaming application. And how does this attack work? It works through OS level shared resources. And it turns out that the operating system actually allows this zero permission application to query how much memory is consumed by this browser application. And by monitoring the memory usage over time, you can build a fingerprint of the website you are visiting. Okay. So that was an example of OS level shared resources. So here's another attack that exploits CPU level shared resources. Imagine I'm running a website, and I'm hosting the website on Amazon EC2 machine. And the way it works is I'm going to rent a virtual machine from Amazon EC2. So this is virtual machine instead of operating system, but the idea of the attack is the same. And in some sense, actually, virtual machine monitors are supposed to offer even stronger isolation than operating system. And yet, they fail. So in this case, this attacker VM, which is co-resident on the same physical machine as your website, can learn your encryption keys that you are using to, let's say, encrypt your HTTPS communication. So you'd think that this shouldn't be possible, right? But it turns out that both of these VMs will be sharing the same CPU cache, and the information leakage can happen because of cache timing attacks. I won't go into the details of the attack, but essentially, the isolation isn't perfect here. Okay. So what I've said is that enforcing isolation is difficult. But I haven't said that it is impossible. In fact, if you are really, really careful when you program your operating system and virtual machine monitor, it may be possible to enforce perfect isolation between these applications. I mean, in reality, it depends on what architecture you are running on. But suppose we are able to actually enforce perfect isolation. Even if so, there's still the big issue that the operating system still needs to be trusted. In other words, we say that the operating system is part of your TCB, where TCB stands for Trusted Computing Base. So what's wrong with this? It is very wrong, because if you think about operating systems today, there are these humongous beasts. Like the Linux kernel today consists of 19 million lines of code. And as we all know, the security of your system is only as strong as the weakest link. So if any component in the Linux kernel, let's say a printer device driver, is compromised, then everything gets compromised, because all of the operating system is running at the same privilege level. And perhaps unsurprisingly, there are tons of kernel vulnerabilities. And if you search online, you'll see those in these vulnerability databases. OK, so in the spirit of the coming Christmas, so trusting the operating system is really a bad idea, because the operating system is a big TCB, and it opens up the attack surface. All right. So that's one big problem we face. Another problem is the possibility of physical attackers. So imagine that your computing platform is hosted in the cloud, in a data center. And the cloud company may have malicious insiders, or there may be intruders to the data center. And when the attacker gets hold of the physical machine, he can do much powerful attacks. For instance, he can tap memory and system buses. He can snoop memory. And he can learn the memory contents as well as the addresses of the data that you're accessing. There's also indirect observation attacks, where you observe variables outside your system, things like timing, power, heat, dissipation. And through these side channels, you can also learn sensitive information. And other than confidentiality attacks, there's also integrity attacks, which I won't go into details about. OK, so to quickly recap, I've talked about two big drawbacks with the traditional approach. One is that the OS is a huge TCB, and the other is that there's the possibility of physical attacks. So whenever there's a problem, there's Intel. I mean, there are also other processor manufacturers, but I'm going to take Intel as an example. So now Intel comes and says, OK, you should not trust any software stack. And you should not trust the computing facility that's hosting your computer. So who do you trust, right? And the answer is obvious. We should trust Intel. OK, so Intel's idea is to build this secure processor that will protect your sensitive application, which we call an enclaved application. OK, so an enclave is an isolated sandbox. So this enclave application will be protected from any software adversary, including any other application, as well as the entire operating system. And also, this enclave application will be protected from any physical attacks as well. So this is kind of the dream secure processor that we want to be able to build. But of course, the reality is harsher. If you look at Intel's SGX technology, it sort of does the job, only that it has some leakages. OK, so I'm going to talk about these leakages in a bit. But I want to mention that before I do that, I want to mention that some of these leakages, it turns out, can be patched at the software level without having to change the hardware architecture, whereas other leakages cannot. OK, So first, let me talk about software attacks. Okay, so here the operating system is your adversary. And I'm going to talk about these two arrows, information leakage, one by one. So the red arrow is the channel where the operating system can observe the page-level memory accesses of the enclave application. So I'm going to explain what this means. OK. So as we all know, our computers have a limited amount of physical memory. And if your application needs many memory pages, then some of these memory pages will be resident in physical memory, whereas others will be paged out onto disk. OK, so disk provides cheaper and larger volumes of storage. So this process is called paging. And if your enclave application needs to now access a memory page that's on disk, it will introduce what's called a page fault. OK. And it turns out in Intel's architecture, the enclave application cannot service the page fault by itself. And even if it can, it may be a bad idea from an architecture perspective to have the enclave application process these page faults, because this is just duplicating the functionality of the operating system. OK, so really the enclave application will ask the OS for help to do this page swap. So in this case, it tells the operating system to swap out page number 2 and swap in page number 5. And the operating system will do the job. So all of these memory pages are encrypted, and the secret key resides in the secure processor. So therefore, the OS cannot easily see the memory contents during the page swap. But unfortunately, the operating system will be able to see these memory addresses, in particular the page-level memory addresses during this process. And so this is essentially page-level access pattern leakage. And it turns out there has been many papers that show such access patterns can leak large amounts of sensitive information. And there are many papers. I only cited one more recent paper here. This is a very nice work by a group of researchers from UT Austin and Microsoft Research in the past Oakland. OK. OK, so this is unfortunate. But the good news is that we believe that this page-level access pattern leakage can be patched at the software level by implementing what we call a page-level ORAN. So if you haven't heard of the word ORAN, it stands for oblivious RAM. Oblivious RAM is an algorithm that helps you to provably obfuscate memory access patterns. And 20 years ago, this was believed to be a purely theoretical result, and there was no hope of deploying it in practice. But recent work has made enormous progress, and today ORAN is really practical. OK. So since actually no one has their hands on Intel's SGX processor, so this idea needs to be confirmed when Intel actually releases their secure processors. But we believe that there's reason to believe that this can be done. OK. So there's also the blue arrow, but I won't go into the details. Essentially, there can be other channels like cache timing attacks. And we've been chatting to a bunch of architects at MIT, and they told me that by leveraging cache timing attacks, they can compromise the signing enclave. I'm not going to try to explain what the quoting enclave. I'm not going to explain what the quoting enclave is, but it's the root of trust. And if you compromise the quoting enclave, all hope is gone. OK, so this is a potential cache timing attack. And then, I talked about software attacks just now. And there's also physical attacks. And these are just like some of the classical physical attacks. But it turns out because Intel SGX encrypts and authenticates memory, you cannot easily snoop memory contents from a physical attack. But you can learn memory addresses by observing the memory bus. And you can also do these side channel attacks like measuring timing, power, heat dissipation, and so on and so forth. OK, so I wanted to mention that actually this memory address leakage problem here So here it's in the context of a physical attack. This has been solved in the recent academic literature. In particular, we have demonstrated that it's possible to build an ORAM inside the hardware and achieve only very low overhead. In particular, over a set of standard benchmarks, the average slowdown is about 2x. And this is really nothing for security, because if you think about, let's say, type-safe programming languages like Haskell, Python versus C, there's easily 10x overhead there. So 2x overhead is really nothing, and plus you only have to incur it for the sensitive application, and not everything. So there have been 2 secure processors that have been built. One is Ascent from MIT, and then the other is Ghostwriter, which was work when I did back at Maryland, and in collaboration with folks at Berkeley and UT Austin. So I won't go into the details of ORAM. ORAM can be the topic of a separate talk. OK. So this is what to quickly recap, this is what I just covered. The ideal secure processor and what we have in the real world. While Intel actually is quite careful about what they claim they defend against. So they're smart people. They know about these attacks, and therefore, if you read their specs and white papers online, they don't make exaggerated claims. All right. OK, so in the interest of time, I'm going to skip through this. And I will quickly talk about formal abstractions in 5 minutes. And I'll basically only have time to talk about what we did at a high level, and then we'll go to the entertainment session. OK. So one big question is, what does these secure processors actually offer, right? What is their theoretical expressive power? How do we think about these secure processors? To understand this, I'm going to try to model these secure processors in the universal composability framework. And I'm going to very quickly explain universal composability here. So in the real world, suppose we have a distributed system consisting of multiple parties. So I'm going to be explaining this from a slightly somewhat different perspective, from a programmer's perspective. So imagine I have to program this distributed system, and the distributed system consists of multiple processes that interact with each other, and potentially they speak crypto to each other. So as a programmer, the system is really difficult for me to program because there are all these crypto protocols going on, and I don't want to think about crypto. So what UC lets us do is that let's abstract away the crypto. Okay. Think about a world where there's no crypto, and the crypto is actually replaced by this happy trusted authority, and these parties are just communicating with the trusted authority. Okay, so this will help me reason about the security of these distributed systems. And it turns out, actually, I want to mention that there's tons of programming language literature in this world. Programming language doesn't allow you to reason about this world, but you can reason about many security properties like information flow, in this world. Okay, so the nice thing about UC is that it tells you that when you really instantiate this trusted authority with real-world crypto, every security or insecurity property in the ideal world will be preserved in the real world as well. Okay. Okay, so that's UC simulation. So how do we understand these secure processors? One way is to look at what instruction sets they offer. On top of the standard x86, secure processors offer a suite of underlying security building blocks. Things like quote, extend, seal. I'm not going to try to explain these. And in fact, if you don't understand what these things mean, that's right, because no one really does. And that's partly why these systems are difficult to program, because if you are the system architect and you are developing API support for trusted hardware, you have to actually be designing cryptographic protocols, and no one knows how to program crypto in the real world. So therefore, why don't we think about trusted hardware using some, cleaner abstraction, and such that maybe we don't have to think about the crypto as is. So that's what we do with the UC. Okay, so I won't go into the details of our UC modeling. I'm just going to say that we try to model SGX using the UC approach. And once we do that, there's many nice things we can do. We can kind of try to understand the expressive power of these secure processors. So we show that FSGX, which is our SGX trusted functionality, can allow us to realize things like secure multi-body computation, secure outsourcing, multi-body computation. In some sense, these are unsurprising because from the theoretical literature, we know very well that even with minimal, possibly stateless trusted hardware, we can circumvent a lot of these theoretical impossibility results, and we can realize very strong primitives like simulation secure obfuscation or simulation secure functional encryption. So there are many papers. I'm getting ahead of myself. There are many papers on these topics. I won't go into the details. But here, actually, maybe one interesting observation is that FSGX seems to offer something stronger. One interesting observation is like the theoretical explorations on trusted hardware seem to have evolved somewhat independently from what the architects are doing in the real world. So that's perhaps why the real world, the architects are doing something different. Okay, so stateful obfuscation is a primitive where, so I'll spend 1 minute on this application. Imagine there's a hospital that has a sensitive data set consisting of medical records, and suppose there's a database program. And the hospital wants to let researchers query this database. So what it will do is that it will obfuscate the database as well as the database program and send this obfuscated program to a server running in the cloud. And once the setup is done, the researcher can query this obfuscated database, this obfuscated program, and and Adam said that we want to be able to ensure differential privacy. So therefore, you make query, and you consume your privacy budget, and after a while, your privacy budget is depleted, and at this point, the obfuscated program should no longer return anything. You should only return bot. Okay. So if you think about it, this is not something that standard obfuscation can do because it requires the obfuscated program to be able to remember state. Okay, so it turns out that if you have traditional obfuscation, if you have stateless hardware, it's impossible to realize something like this. So we show that FSGX can allow you to realize stateful obfuscation. And let me conclude my talk by saying that there are many advantages of such formal modeling. It can aid our understanding. It can allow us to make theoretical explorations of the expressive power of trusted hardware. It can help us design provably secure applications on top of trusted hardware. It can also help us design the provably secure processor itself. Okay. In our paper, we also cover many other topics, like does trusted hardware obviate crypto? I promised my co-authors that I'm going to announce the Helio system, where we leverage a cluster of SGX machines, and we allow the data analyst to submit a program that's going to be run on a big data set, like a data set of medical records, and the data owners can label their data with respective privacy policies. And we will execute the program and enforce these privacy policies in a formal sense. OK. So thank you very much. And Christmas themed, thank you. And